In this lesson, we're going to look at how do you decide whether two variables are positively correlated, negatively correlated, or not correlated. So let's start off by thinking about an example of two variables, height and salary. And we're going to start talking about the population correlation. So the population correlation is, imagine you take every single person in the world, in the population, and you put them on our scatter graph. And I don't know what the scatter graph would look like. Might look something like that. And then the question that we want to ask is, are these two variables correlated? So you're probably going to assume that if you take just the adult population, then there's no correlation between height and salary. But in order to work this out, we're not going to be able to survey every single person in the world. So what we do instead is we take a survey of just a few people. So in this example, I've just surveyed 6 people and put them on a scatter graph. Going back to the population, we're going to introduce a new symbol which is called rho. And rho is the population correlation coefficient. So let's write that down. So rho is the correlation coefficient that I'd get if I sampled everyone in the entire population. So we've got our sample of 6 people here, and we're going to try and use this scatter graph, this data, to work out whether the population is positively or negatively correlated. So let's suppose that we got R is equal to 0.4. Now notice that I'm using R now. That's because R is the sample correlation coefficient. Okay, so if we were to look at our diagram of our correlation coefficient between -1 and 1, in the middle we've got no correlation, and we've got our sample correlation coefficient as 0.4. So just from this sample, it's not obvious whether 0.4 is close enough to 1 to convince ourselves that the population is positively correlated. Obviously, if this was really close to 1, then we could be fairly confident that there is a positive correlation in the underlying population, which we took our sample from. Well, in order to work out whether 0.4 is close enough to 1, we're going to have to go to page 37 of the formula book and look at the product moment coefficient tables. And it turns out that the sample size is going to affect whether we can conclude that there is a positive correlation or not. So we're going to look at the rho, which is related to n equals 6, because there's 6 data points in the data that I'm looking at in the sample. And this word level stands for the significance level. So let's just work at the 10% significance level for now. And we'll look at the effective significance level later on. So what this table tells us is this number here is the minimum value that R would have to be, our sample correlation coefficient, in order to conclude that there's a positive correlation. So if we put that on our scale here, 0.6, if we had R is greater than 0.6, then we can conclude that there's a positive correlation. And we call this our critical region. And you should recognize that word already from Year 12 statistics. The critical region is the region in which we can reject H0. So let's try and formalize this a little bit. Work by doing a hypothesis test. So our null hypothesis is always that the population correlation coefficient is 0. So rho is equal to 0. And you could, if you wanted to, write in brackets just to help you remind what remind us what that is, that the population correlation is 0. So there's no correlation. Let's put that underneath. And that's always going to be H0. No matter what hypothesis test we do, we're always going to say that H0, our null hypothesis, is that there's no correlation. And then we're going to try and prove that there's a positive correlation in this case by trying to see whether R is big enough or not. So in this case, because we want to test whether there's a positive correlation, we're going to test rho is bigger than 0. So that would mean that the population correlation is positive. So from this table, let's suppose we're working at the 10% significance level. This table tells us that our critical region is R is bigger than 0.6 because that's close enough to 1. Well, in this case, we're at 0.4, which is less than 0.6084. So we're not close enough to 1 in this case. So we can't conclude that there's a positive correlation. So let's write that down. So we're not going to reject H0. And in this case, if we don't reject H0, that means that we're concluding that there's no correlation. So conclude in fact, I'm going to reword that actually. I'm going to word it as there's insufficient evidence to suggest that there's a positive correlation. And I'll explain why in a second. Conclude that there is insufficient evidence to suggest a positive correlation. The reason why I'm wording it like that is I'm not actually saying that I certainly know that the population correlation coefficient is 0. The reason why is because I've just got a sample. So I can't be sure that it's not just the case that I've chosen a sample that leads me to believe that there's no correlation. I might have taken a different sample or a bigger sample and concluded that there was a positive correlation. It's worth noting at this point what the effect of the sample size is on our rejection region, our critical region. So if we looked at, for example, a sample size of 20, our critical region would have begun at 0.299. So our critical region would have been all the way down here. So if our sample size had been 20, we actually would have been close enough to 1 because 0.4 would have been bigger than 0.299. And the reason why that's the case is because when our sample size gets bigger, we find we're more confident that our sample correlation coefficient R represents the population correlation coefficient rho. So that means that we can say that it's easier to reject H0. We're more confident with our analysis. And it's also worth noting what the effect of the significance level is on the critical region. You should already know that when you reduce the significance level, you reduce the size of the critical region, making it harder to reject H0. So if we reduced our significance level to 1% here, then our critical region would have begun at 0.88. So we'd be all the way over here, and we'd need values of R which are bigger than 0.88. So we would have been even further away from rejecting H naught. It would be really hard to reject H naught if we were working at the 1% significance level.